We have an example problem here. White light between 400 and 700 nanometers is incident on a 600 line per millimeter diffraction grating. What is the width of the first order rainbow on a screen 2 meters behind the grating? All right, so diffraction grating, that means the equations that apply are d sine theta is equal to m lambda, and y sub m is L tangent of theta sub m. The theta in both of these equations is the same. D means the distance between the slits, which we can get from this 600 lines per millimeter. Now, D is not 600. D is a distance between the slits, so we actually need to invert this. D will be 1 over 600 millimeters. So if I plug that in, and I will want to convert this to meters, or at least watch your units very carefully. So to convert, this is telling me that D, it keeps going, those sixes keep going around. So I have this in meters, 1.6667. I do want to take those decimal places beyond the 2 sig figs that we're going to be expressing our answer in. So we know D. This 2 meters is L. If you recall, L in our equation is the distance from the slits to the screen. So we have, it tells us that the screen is 2 meters behind the grating, and hence that is L. Now, if you do not recall the video clip, the demo for the diffraction grating, specifically the one that had white light first, when that white light was shining through a diffraction grating, we still saw the white light in the middle, and then over to the side, on both sides, we saw a rainbow. That was the violet or blue end over to the red. Violet to red. Each wavelength is diffracted by a different amount. And ultimately, that's what this is getting at. And sorry, that white light is in the center. So this question, what is the width of the first order rainbow? First order means m equals 1. So the first rainbow we see to the right or left of that center. They're asking us for how wide this is. Now, coming back to the right to our equations, D is the distance between the slits, which we know. Wavelength. Well, we have a range of wavelengths. So that's also why we get a range of how far they diffract and spread out on the screen. M is going to be 1. Y in these equations over here is the distance from the center to whichever part of this rainbow we're talking about. There's a Y1 for every single color in there, for every single wavelength in there. So it turns out this end, this left end, is going to be where the wavelength is smallest. The smallest wavelength will be diffracted the least. This end over to the right is going to be for the longest wavelength. So if we find Y1 for a wavelength of 400 nanometers, and then the same thing, y1 for a wavelength of 700 nanometers, then we can take the difference of those y1 values, and that will give us the width of that rainbow. So coming back to our equation, we know D, we know m and lambda, so we'll be able to use this top equation to find theta. That is the same theta as in the tangent, and we know L. So if we use the top equation first to find theta, then we can use the second equation to find y. So sine of theta is going to be lambda over d. Because remember that we're talking m equals 1, because the problem specifically states first order, the first rainbow on either side. So coming over down here, sine of theta 1 for violet light will be the 400 nanometers divided by D. Now we got D from this grating, the 600 lines per millimeter. We had to invert that to find the actual distance between the lines. I do need lambda and D to have the same units. And then I can take the inverse sine of both sides to get theta. So I'm getting 13.89 degrees. Now, as a reminder, with the diffraction gratings, these angles are not small enough to use the small angle approximation. That's why we do have to keep sine of theta and tangent of theta in the equation. So y1, I'm going to, up in this right top box, y1 will be L times the tangent of theta 1. L is 2 meters. And then we're going to take the tangent of our angle. So I'm getting 0.4945 meters. What that means is that the distance from the center to the edge of this violet, where the rainbow starts, is 0.4945. And that's true regardless of which way I measure, to the left or to the right. So we need to repeat the process for the 700 nanometers wavelength. So this is still a sine of theta, but now we have a different wavelength, which means we're going to get a different angle. So theta 1 inverse sine of 700. Oops. I'm getting 24.83 degrees. So that's a big difference in angle, but that's okay. We can now find out where this particular end of the rainbow, how far it is from the center. I'm getting 0.9256 meters. So coming back up to my picture, from the center over to the right end of the rainbow is 0.9256 meters. And that's true measured on either side. So the width of the rainbow is going to be the difference. So where the right side of the rainbow is minus where the left side of the rainbow is. And then writing this in two significant figures, I'm getting 0.43 meters, which of course, if we wanted to, we could write it as 43 centimeters. So that rainbow on the screen on either side would have a width of 43 centimeters. That's what this represents.